let's get started. Everybody, thank you for coming. Virtual seminar series with IGCP648. Our brave leader, Luc Doucet, is finally taking a little vacation. So Ross Mitchell here to the rescue. Today we have with us Bernhard Steinberger. He's a geodynamic modeler working at GFZ German Research Centre, Geosciences in Potsdam in Germany. He got his undergrad in Munich in Germany and PhD with Rich O'Connell, I believe, at Harvard University.
Yes.
Yeah, the late Rich O'Connell, late and great.
Yeah.
Bernhard's worked all over the world. He's worked multiple places in Germany, Taiwan, Boulder, Colorado, Japan, and in Norway, obviously.
Yeah.
His research really is multifaceted, from mantle flow modeling, but also very much parameterized by observations such as the geoid, topography, lithospheric stress to constrain those models. His research interests are many, but the ones we want to highlight are mantle plumes, generation and interaction of large-scale mantle flow and the lithosphere, spreading ridges, relationship of mantle flow to plate motions. And he's also been involved, my personal interest, in absolute reference frames, allowing the motions of plate motions to be coupled to the mantle. And he's done stuff as well in how mantle flow can actually deform the lithosphere, cause uplift, subsidence due to dynamic topography. And I'll finish with my favorite topic. Bernhard's done a lot ever since his earliest years at Harvard on true polar wander, showing how mantle flow changes the orientation of the entire Earth relative to the spin axis. So today, Bernhard has a very exciting talk to us for a paper that I believe is published today, about an hour ago, by Nature.
In about an hour from now.
In about an hour, okay.
Yeah,
so yeah. You have to listen to Bernhard now because you can't read the paper. So absolutely perfect timing. As soon as we're finished here, you can search, and Nature will be pretty good about lifting the embargo and putting it online. So we couldn't have better timing. We couldn't have a better guest. And we got 40 people. So Bernhard, please, the show is yours.
Yeah, okay, thanks, Ross, for inviting me. And yeah, actually, Ross invited me some time ago, but then I thought, well, I don't have really anything relevant for supercontinents. But then I saw that many of the talks given weren't really so much about supercontinents either. Then I thought, maybe I can still contribute something. So I contacted him again, and luckily it worked out that we found this slot for me to talk. So now I'm gonna share my screen, and I hope that works.
Great.
Teilen, share, and then I need to go onto full screen. Right. And yeah, before I start, I should say I had a few days ago, I had twice that my computer suddenly shut down. So I hope this won't happen during the talk, but if it does, usually it will come up again within 1 minute or so. So don't end the seminar if I'm suddenly gone, but I hope it won't happen. Okay, so now let's come to this story sort of, and we'll start in, Ross just mentioned that I was in Norway before, and this story really starts in Norway around 2008 when I was working with Trond Torsvik. And then at some point, Trond was going around our section and say, well, he has this guy from Utrecht who would like to work with him. And yeah, he seems like a really good guy, but he's gonna want to do so much field work and in all those exotic places, and he's gonna be really expensive to have him. And then he went on to say, yeah, it's really nice to have modelers like Susanne Beuter, who was there, and me. You just give them a computer and a desk and they're happy modeling along. But then in the end, he still found the money to hire Daue and to give him all the field work. And yeah, so this is what I'm talking about, is sort of but it was not only about going to exotic places, but the thing was that Douwe also had a sort of a grand scheme, a grand plan in his mind, how to put everything together. And this is sort of what I'm talking about today, is part of it, or this is sort of a synthesis of a lot of this field work, which Douwe has been doing since then in the last 13 years. And since I'm a modeler, I won't understand too much detail about the field work. So I'll talk about it a bit in the beginning, but I'm not the expert on this. So that's why I will focus more on the modeling in the later part. So yes, so the basic mechanism is shown in this picture, but I'll come back to this later. Right. So so this is the Douwe's project, and the question is about geodynamic processes to trigger the formation of new subduction zones, because he found that around that time, around 104 million years ago, there were a lot of new subduction zones in the western Tethys region. And based on metamorphic soils and also ophiolites, which are due to supra-subduction zone spreading, the conclusion was that the metamorphic soils predated the supra-subduction zone spreading. And this was taken as an inference that this was not locally, but it was remotely, by remote stresses, was induced the subduction zone. So the subduction started first and then the spreading afterwards. So this precludes a spontaneous subduction initiation. So subduction resulted from far field forcing, was the conclusion. Now the question was, what could be the source of this far field sourcing? Yes, and those ophiolites, they formed at north-south trending supra-subduction zone ridges. So really the subduction was going east-west, because the subduction zones trended north-south. It's known that the plates in the Tethys region, they were moving northwards, but what could be then the reason for this east-west subduction zone initiation? And so the idea which we pursue in this work is that it could be due to a mantle plume, and the mantle plume down here near Madagascar. Now the question is, of course, a mantle plume starting here, how can it cause, it could perhaps push those two plates apart, but how can it cause plates to converge up here? So this is in 110 million years ago. There was this subduction zone at the northern end of the Neo-Tethys, but nothing here at its western end. But then about 105 million years ago, you have these subduction zones at the western end of Tethys. And you have the plume here, that it came actually to the surface at 90 million years, but at 105 million years ago, it was already beneath the surface, and it could have already pushed apart the plates according to our modeling. So kinematic restoration of the new plate boundary at 105 million years. Neo-Tethys subduction zone runs from triple junction eastern Mediterranean round to western Indian Ocean. And then it transitions into a rift ridge that opened the Mascarene Basin down here. And the subduction initiation predated the Morondova lip emplacement by 10 to 15 million years ago. But we thought of maybe it was still this Morondova lip that gave rise to this motion. Right, then the Morondova plume, whether it could have caused hemispheric plate boundary formation. In order to develop slabs long enough for self-sustaining subduction, about 100 kilometers requires only about 1 degree of India-Asia rotation. So could this plume push have caused this much of rotation of the plate? So not only the plume pushing India plate north, but also causing a relative rotation of the India and Africa plate. Then, so how it developed further, then the subduction zone continued, like shown here 70 million years ago. And then this is a present day So there are all these remains of these subduction zones. They're now from Oman to Turkey, in the region where Tethys has been closed. So that's where you can find all those remains from which you then can infer these plate reconstructions. Right. Now, yes, before we get to this plate rotation, we go back again to around 2011. So the question we asked at that time is whether this Morondova plume could perhaps cause the India plate to move northward fast enough, to explain this acceleration of plate motion. Because if you look at the plate motions, Western and Eastern Himalaya, you see a speed up, especially in the Eastern Himalaya at the time of the Morondova lip, and another speed up at the time of the Deccan lip. So the question we were asking first is whether the plume could really cause this speed up of plate motion. This is, yeah, for another reconstruction, you get basically something similar. You get always these two speeds ups. This is a relative convergence, which is better known, but if you go to absolute plate motions, you also, at least at the Eastern syntax, you find that you also, for the absolute Indian plate motion, you have these speeds ups for these two plumes. Now, what we did is, we did some numerical model calculations, first with my own code, which doesn't have lateral viscosity variations, and computing the mass flux of the different plumes with time, and then computing how much acceleration they could give. So that dotted or dashed lines, they are the maximum acceleration if you have the plume at the side of the plate and always right at the side, and some simple hemispheric geometry. So you see for Deccan, because it's a smaller plate at this time, the Indian plate, you can get up to 9 centimeters. Speed up for Morondova, you can only get about 3 centimeters, but it gets a lot less the motion, and it goes down again if you take the actual plate geometry into account. So the basic conclusion was, at least for Morondova, it's not sufficient to explain by itself all this plate acceleration. You can get perhaps 3 centimeters, but this is less than the actual plate. Now, this is without lateral viscosity variations. We then also did some calculations with the Sitcom S code to include lateral viscosity variations. And these are work which has been done by René Gassmüller. He was actually, at this time, he was an undergraduate student in Jena University, and he came to do an internship with us. And so it was quite impressive for him to do that during this internship. And you may know him, he's now one of the main developers of the aspect code. But he was already, at that time, he was very capable to do that all by himself. Now, what it shows basically is that when you have this plume with a low viscosity reaching the surface, then this decouples the plates. So this means that with the actual rheology of the plume is even less capable of pushing the plate. So this semicircle radius of 33.7 degrees, this corresponds to more or less a plate size, Indian plate size at the time of the Morondova plume. You can only get about 2 centimeters per year for a short time, and then it drops to 1 centimeter a year. So again, the conclusion was that it's probably not enough to push the plates to that speed which they reached. But so the conclusion in that paper was that you may need some combination with other effects, like the plume feeds into the asthenosphere, makes the plate slip more easily, and then is sliding more easily. It could then cause a subduction. Subducted slabs can pull the plates more easily. So this was our suggestion, that this combination might work. But then coming back to this initiation of subduction zones, now we thought, okay, you only get 2 centimeters per year for a few, for a few million years. But then on the other hand, you only really need, in order to initiate this subduction, which could then become self-sustained, you might only need 100 kilometers of convergence. So is it something you can get with a plume? And in order to address that question, now I didn't do any more real numerical models, because thought I do something simple first. And so that's really only the very simple models which I present now. So it's sort of semi-analytical models to make it plausible that this could be a mechanism. And in order to see that, I show you a YouTube video which I made. So do you see it now?
We see it now.
Okay.
Excellent.
Right. So it's sort of a tabletop experiment. So I made some cutout of those two different plates, the African and the Indian plate, to visualize how when the plate pushes, when you push them apart here, how you can actually get convergence up here. So this is this small circle is supposed to be the plume where it impacted. So you have here like the African plate, here you have India, here you would have Madagascar, and this is what happened around. Plume started pushing around 105 million years ago and reached the surface around 90 million years. But then while it was pushing up, it could already push the plates apart. So this is just in principle to show how you can get this mechanism. And then later I will do some calculations how much the effect actually is, because it's not as much as shown here. So what happens is, yeah, if you push the plate and then you see up here, it actually moves the other way. So you can try that with any piece of paper, and it always works like this. If there is a equal friction everywhere, then it also works the other way. Then because you push down here at the lower end of the boundary, then the upper end of the boundary goes the other direction. So you get, on one hand, you get a displacement, but you also induce a rotational component. And if you have two plates, then of course both will move and they will converge on the other end. Now the thing is that the convergence you get this way is less than what is inferred from the actual convergence. So the actual plate boundary that's convergent is actually longer. And how can you do this? So what I did is that I made a stronger coupling of the plate with the underlying mantle by pushing this penny, putting this penny on there. And then this is supposed to be the thicker craton which couples the underlying plate to the mantle. And then you see, because it's coupled here, then all this part is convergent and only this part is divergent. But of course, it only works in this idealized case that you have the coupling basically only here, everywhere else it's decoupled. So yes, that was the experiment. So now I could basically stop, because that's basically the story. But I think we still have some time. So now let's get a little bit more quantitative, and it's not going to be very difficult, I hope, but I think a little bit of math and physics should be in there still, a little bit more. So there are two questions I'm trying to ask. For one thing is, I say there is no friction at the plate boundary, so I don't consider that it's friction, and we only say there's a plume pushing apart, and then it's moving, the plates are moving freely over the underlying mantle. So how much plate motion or rotation of the plates can be caused by the spreading of the plume head in the asthenosphere, and particularly to see whether this amount of convergence would be sufficient to induce 100 kilometers of convergence, which could then turn into self-sustained subduction. And secondly, if the plume push force is balanced along the convergent plate boundary, how much stress can it be caused? So that's sort of the other extreme. You don't consider that the plume has friction with the underlying plate, but you just, if you remember this penny, you just say you push on one end and all the force the plume pushes is transferred to the plate boundary on the other end. And this would be your force balance. And then you can sort of get the maximum force or stress that can be induced by the plume. So these are the two calculations I'm going to show now. Right. So this is a more quantitative approach to the kitchen counter experiments. And we say, well, the question we are asking is, you have this plume head, which you say is 500 kilometer radius, or 1,000 kilometer diameter, which is something which, for example, by Griffith and Campbell, I think they suggested this is a right size, suitable size for a plume head. And we say that we feed this plume head into the asthenosphere, and this asthenosphere then pushes, it induces a parabolic flow profile in the asthenosphere, and this pushes then the plates. And we say that you have the plume-induced flow in the asthenosphere, and this causes a plate motion. So what is the plate motion which is balanced with this plume-induced flow, such that the forces are balanced? Right. So start the calculation is first we say that the total volume flux rate, which you get by having the plume head flow into the asthenosphere, is 2/3 times the velocity times 2 pi times distance from the plume center times the thickness of the asthenosphere. And the 2/3 comes from assuming a parabolic flow profile. Now we can integrate this volume flux rate with time and have the condition that the time integral equals the volume of the plume head. So we get the time integral of the velocity is the total displacement in the middle of the asthenosphere, and by setting this at time integral equal to the volume of the plume head, we get this equation, yes, for the displacement, just by setting the time integral of the volume flux rate equal to the volume of the plume head. And then we can calculate the displacement gradient at the top of the asthenospheric channel. So the displacement gradient with this parabolic flow profile is 4 times x plu divided by hc, where the hc is the asthenospheric thickness. And when you assume asthenospheric viscosity, then you calculate the time integral of the stress that acts on the plate. So we got this now, and in order to compute the torque of the plate, you do some integration of the stress with vector product with the radius, and then integrate over the area of the plate. And we say we only integrate within 2,400 kilometers of the plume, because eventually the material will of course not stay in the asthenosphere, but it will flow down into the lower mantle. And from some other work I gather that, or some simple estimates gather that 2,400 kilometers, which is similar to the depth of the mantle, would be sort of an appropriate value. So in this way we can compute the torque that's caused by the plume. So it's radius times the x plume. This is the displacement in the middle of the asthenosphere. And if we set this in, this x plume, then this is the value we get for the torque of the plume. So that's something we can relatively easily compute if we have the geometry of the plate, right? Now we said we want to balance this with the torque from the plate motion. Now for the plate motion we have a different setup. We have here the displacement of the plate, and in this case we don't have this parabolic flow, what is it, Poisson type flow profile, but we have this shear flow, the Couette type flow. And again, we can get the displacement gradient is the x of the plate motion divided by hs, whereby this is the shearing depth of the asthenosphere, not necessarily the same as the depth before. And then we the time integral of the stress is again multiplied with the viscosity eta 0, and we can again then compute the plate motion torque by integrating this x of the plate motion a cross product with the distance, and yes, and the plate motion then can be expressed as omega, the plate rotation times radius. So this is, if you take omega as the plate rotation, this is a torque, and then if you have it this at the time integral of the plate rotation, you get the time integral of the torque. Now we want to set this time integral of the plate motion torque equal to the time integral of the plume torque. So we find omega such that they're both are equal, and well, the way you can do this is then you you take you take three different omega, so around each of the axes of the Earth. So one about the North Pole, and the one x-axis is at 0 degrees north, 0 degrees east, and y-axis at 0 degrees north, 90 degrees east. And for each of those plate motions, you compute the torque, and then you can say that the total torque, depending on the plate motion, can be expressed as the sum of these three torques. And you can then set this Plume torque equal to the plate torque. And you can probably all see that this gives them three equations for three unknowns, omega x, omega y, omega z. So you can solve for this, and omega 0 cancels out in the end, and eta 0 nicely also cancels out. And so you get a result that only depends on geometry. So this is a simple calculation that you can calculate how much the plate moves, and it only depends on plate geometry and the assumed size of the plume head. Now, this is what the result is then for the actual geometry, which is derived from these plate reconstructions from Dower. Here is where you say the plume hit is based on a reconstruction when the lip center, which is currently assumed at 46 degrees east, 26 degrees south in Madagascar, is reconstructed to 87 million years ago in a slab-fitted mantle frame. Right, we use a slab-fitted mantle frame, but it's that actually works quite well, because if the present-day position of the plume is in Marian hotspot, and we calculate based on my mantle flow models where you would expect the plume to be 87 million years ago, it's not exactly at the right place, but it's not too far off either. So this is a reasonable assumption, and that's why I think the slab-fitted mantle frame is also reasonable. But of course, you can also use another reference frame and have the plume then in a different location. The relative location of the plume would obviously always be the same relative to the plates. So you always have it such that it fits with the present day Madagascar plume location here. Right. Now, this is the plate motions, individual plate motions, but we are interested in the convergence. So we put this into an Africa fixed reference frame, and then we see that you get convergence up here. You get the plate rotation pole up here, and you get divergence, a lot of the plate motion. Now, this is getting problem is that you get too short convergence compared to the observed convergence, which is really all the way down to here. Now, question is, how can we get this? So now, you remember my video with this penny? The idea is to fix, to make the coupling of the India lithosphere more strongly. Now, how do we do this in a more mathematical way? Is again, get back to the velocity gradient and shear stress, which is force divided by area. And what we do now is I use a mantle viscosity profile, which is so not just the asthenosphere, every shearing over the asthenosphere, but I use a mantle viscosity profile, which is derived from one of my previous papers. And I say that the shear stress has to be independent of depth, because it's the same force that's always transferred down. So that means that the velocity gradient is then inversely proportional to viscosity. And the total velocity gradient integrated with depth is equal to the velocity. It's equal to the velocity if we integrate it down to the maximum viscosity. So in this way, we can define equivalent asthenosphere depth, which for this viscosity structure is equal to 203 kilometers, just by solving this for HS, right? So now, how do we get, so this is now for one particular lithosphere thickness, but we can now solve this shear stress for this shear stress by dividing by this integral. So you get, when you solve this for F over A, you get F over A is the velocity at the surface divided by the integral over 1 over the viscosity. And you see, if you make this upper limit of the integration depth dependent, so if you have corresponding to different lithosphere thicknesses, then this gets variable. And then the thicker the lithosphere gets, the smaller this integral gets, and the larger the traction gets. So this is intuitive. When you have a thicker lithosphere, it's harder to move the plate over it and you get more traction. So for this viscosity structure, I compute the traction as a function of lithosphere thickness, and this is the resistance factor I get. So normalized to 1 at 100 kilometers, and it's about half as much if there is no lithosphere, and is about twice as much for 240 kilometers. So it's variable by a factor 4 or 5. And yeah, so it's not too much. Now, how do we get the lithosphere thickness? This is first we start with the present day thickness, and I did this in a paper in 2016. I computed lithosphere thickness based on seismic tomography, using here a combination of the Scheffer and Lebedev surface tomography model at greater depth, the grand tomography model. And in order to compute lithosphere thickness, we assign a certain reference temperature profile. So we say this is the reference temperature, sort of an average temperature profile of the Earth. And we assume that seismic tomography represents the temperature variation, so the temperature deviation at a given depth from this reference profile. So when you have like so you can convert the seismic velocity variation into temperature variation, and by adding this reference profile, you get the absolute temperature. And now we say that this absolute temperature, when this reaches a certain given value, which we assign to the base of the lithosphere, then you have reached the base of the lithosphere. Or you can also do it the other way. The way we do it, we assign the velocity, seismic velocity, and then we compare it to this reference profile, and wherever there is the point where they intersect, that's where you have the lithosphere thickness. So if there is a positive seismic velocity, you get a thicker lithosphere. If there's 0, you get the reference value. If there is negative seismic velocity, you can get a thinner lithosphere. So this is how we derive lithosphere thickness, and then we just rotate it basically back in time. So we rotate the India craton back to down here. And yeah, so that's continents just rotating back. For oceans, with the different approach, we'd use a present day backward rotated H-crest and compute the thickness where possible. And then there are large regions of Tethys where the ocean floor has been subducted, so we just assume constant thickness. And then we use this variable lithosphere thickness to compute a variable resistance factor and different cratons. So the idea is then basically you have cratonic coupling here, the Indian craton, and you have the Indian plate then rotating around this craton. So that is what we would like to get. Yes, and yeah, I should say you use present day thickness, but the problem is the Indian craton might have been thicker in the past. So this may be one of the reasons why things not sufficient to get the rotation pole further down, because you see the result is still very similar, because of this small region of thicker lithosphere is just not enough to move this rotation pole of the Indian plate down to where we would like to have it. So now we say, okay, we go to a more extreme case. For whatever reason, it could be that where you have also maybe non-linear effects, or the fact that the Indian craton was maybe thicker at that time, could be that it was much more strongly coupled to the mantle than the surrounding mantle. So what we do is that we just say that coupling is 10 times increased wherever the reconstructed lithosphere exceeds 100 kilometers. So this is this brown area, and it's 1/10 only wherever it's less. So basically, like with this penny, which couples more or less, you get strong coupling here, weak coupling everywhere else. And then in this way, you can get this rotation pole further south. So it's still not down here where you would like it. from the geologic observations, but we can get it further down. And this is the total convergence you can get in this way. So it's a few hundred kilometers up here. And so it might be enough to induce subduction, right? To have enough subduction induced. And what did I want to say? Such that then can become self-sustained. And of course, there might be other contributors like spreading ridges which help. And this would be an additional factor that the plume starts pushing, right? Okay, last point is that I said I wanted to compute how much stress the plume can induce. And we assume a torque that is equal to the force which from the plume head computed, just a rising plume head with a given density contrast, and we say half the force acts on the India plate. So from the force and the distance from 4,000 kilometers from the spreading, now from the pole of rotation, you can compute a torque, and then you balance this torque by a stress along the other side of the plate boundary. And it's a simple back of the envelope calculation. I didn't really do anything more. I can calculate the stress is about 240 megapascal. So this is the maximum stress you can get if you have only those two forces, the plume pushing and the plate boundary resisting. Everything else, sorry, is disregarded, which is the other extreme than what I said before, where I had no resistance here in order to compute the amount of convergence, but only resistance at the base. So this would be sufficient to overcome frictional resistance between subducting and overriding plate, estimated at the order of tens of megapascal. But it only works if the plate boundary is already weakened. So if you have a strong plate interior, this is nowhere nearly enough. So you would have to have a pre-weakened plate boundary somehow, which then the plume can use to push this convergence, which would not be there otherwise. So in reality, only a fraction of the torque will be balanced at the convergent boundary, and the plate boundary already needs to be weak prior to subduction initiation. Right. And so to summarize that, we can plausibly explain this east-west subduction in the Neothetis Ocean by plume push. The plume may drive the formation of hemispheric plate boundaries, and this is now a sort of a long-term inference, is that in the time when there was no plate tectonics before, of course, it has been suspected that plumes may have played a role in the initiation of plate boundaries. So this is another suggestion how plumes may have played a role in the formation of the initiation of a mosaic of tectonic plates at much older times than what we discuss here in particular. Okay, thank you very much.